Hello friends, now we'll discuss TDS equations. So TDS equations are the applications of Maxwell's thermodynamic relations, and there are two important TDS equations. So we'll derive these two equations, and we'll see the importance of these TDS equations. Now the first TDS equation is derived from the Maxwell's thermodynamic relation, and that Maxwell's thermodynamic relation is derived from a thermodynamic potential called as Helmholtz free energy or Helmholtz function, and Maxwell's thermodynamic relation is delta S by delta V at constant T is equal to delta P by delta T at constant V. But we know that the entropy is a function of different thermodynamic variables, thermodynamic parameters. So here let us consider entropy is a function of temperature and volume. So since the entropy is a perfect differential, or you can call it as exact differential, and it is a function of independent variables, temperature and volume, we can write using condition of perfect differential as ds is equal to delta S by delta T at constant V into this dt plus delta S by delta V at constant T into this dV. So this mathematical condition that we can write. Now we can multiply this equation on both sides by temperature T, so that we will get the equation T into this ds is equal to T into delta S by delta T at constant V plus T into delta S by delta V at constant T into this dV. But we know that this part, if you consider, then you will observe that this T into ds is nothing but delta Q. That is whatever amount of heat absorbed or emitted by the system. Then whenever there is a change in entropy as delta S, that is the second law of thermodynamics. So we can write this part as delta Q by delta T at constant V, and we know that this delta Q by delta T is nothing but amount of heat required to raise the temperature of unit mass of 1 mole of gas. It is called as the molar specific heat at constant volume. So we can represent it by CV. So this first part is nothing but the specific heat at constant volume, and using Maxwell's thermodynamic relation, we know that this delta S by delta V at constant T is equal to delta P by delta T at constant V. So we can replace this term delta S by delta V here, this term, by the thermodynamic relation delta P by delta T at constant V, so that we'll get this equation as TdS is equal to CV into this dt plus T into delta P by delta T at constant V into this dV. So this is the first TdS equation. This equation is called as the first TdS equation. Now, what is the importance of this equation? This equation gives the importance that we know that we cannot measure the entropy or change in entropy directly. It is not directly measurable quantity. So we can measure the change in entropy in terms of the thermodynamic quantities which are measurable. So here we can measure the specific heat, we can measure the change in pressure, we can measure the change in temperature, change in volume. So that is how this equation is used to measure the change in entropy in terms of the measurable thermodynamic parameters or thermodynamic quantities. So this is the first TdS equation. Now the second TdS equation can be derived again by using the Maxwell's thermodynamic equation, and that equation is based on or derived from thermodynamic potential called as Gibbs free energy or Gibbs function G. So that thermodynamic equation is delta S by delta P at constant T is equal to minus delta V by delta T at constant P. So again here we can assume that the entropy is now function of uh, two independent variables, temperature and pressure. So here we have to assume that entropy is function of two independent variables, temperature and pressure. And again, since entropy is perfect differential, we can write ds is equal to delta s by delta t at constant p into this dt plus delta s by delta p at constant t into this dp. So again, multiply to this equation on both sides by temperature T, so that you will get T into this ds is equal to T into delta S by delta T at constant P into dt plus T into delta S by delta P at constant T into dp. But again, this T into delta S is nothing but delta Q. So we can write this as T into delta S by delta T at constant P is equal to this delta Q by delta T at constant P. So again, this is nothing but the molar specific heat at constant pressure, because delta Q by delta P at constant delta Q by delta T at constant P will give you the amount of heat absorbed to raise the temperature of 1 mole of gas by unit temperature at constant pressure, and this is nothing but the molar specific heat at constant pressure. And again, this term delta S by delta P can be replaced by Maxwell's thermodynamic equation as delta S by delta P at constant T is equal to minus delta V by delta T at constant P, so that this equation will change to this equation as T into ds is equal to Cp dt minus T into delta V by delta T at constant P into this dp. So this is the second Tds equation. This equation helps to measure the change in entropy in terms of the measurable quantity, like change in volume with respect to temperature or change in pressure and specific heat at constant pressure. That is how these two equations are very important in thermodynamics. I think you would like this lecture. If you like my lecture, kindly like it and subscribe it. Thank you for watching this lecture.